Imagine a world where chemical reactions don't really need intense heat or, harsh catalysts.
Mm.
A world where just a simple flash of light can twist molecules into these impossible shapes, forge new bonds, and create entirely new compounds.
Yeah.
Today, we're diving into that world. Photochemistry. It's where light isn't just for seeing, it's actually a powerful tool for creation.
That's absolutely right. We're going to explore how organic compounds, everything from simple alkenes to quite complex aromatic rings, how they absorb light and enter these incredibly high energy states, these excited states.
Excited states, okay.
And once they're there, they can undergo transformations that would be completely, well, out of reach under normal thermal conditions. It's a field that's not just academically fascinating, but also incredibly important for creating new materials and designing totally novel synthetic routes.
Right, so our mission today is to give you a real shortcut, kind of a backstage pass to understanding the critical concepts here. Think of it as the molecular dance floor, where light is the DJ. We'll try to demystify terms like singlet and triplet states, show you how these ultra-fast reactions play out, and hopefully give you that aha moment about why light chemistry is just so profoundly different.
This is where it gets really interesting. So, let's start with the basics. For any photochemical reaction to happen, the very first condition seems simple enough. The molecule has to actually absorb the light.
Exactly. That's the entry ticket. We're talking about organic molecules here mostly, and when they absorb that light energy, an electron gets this massive energy boost. It literally jumps to a higher energy level within the molecule.
Okay, a big jump.
A big jump. And this often happens in molecules with what we call unsaturated groups, things like carbon double bonds in alkenes, or the CO double bond in carbonyl compounds, even aromatic rings. An electron typically moves from its usual orbital, often the highest occupied one, the HOMO.
The HOMO, right. Up to a higher energy, usually empty anti-bonding orbital, like the LUMO, the lowest unoccupied molecular orbital.
Antibonding. So that weakens the bond.
It can, yes. Populating an antibonding orbital changes the whole electronic picture. Now, once that electron is excited, the molecule can exist in one of two really crucial states: a singlet or a triplet state.
Singlet and triplet. Okay, what's the difference there?
Think of electron spin. You know how electrons have this property called spin, often visualized as up or down? In a normal molecule, electrons in the same orbital have opposite spins. They're paired up. When one electron gets excited in a singlet excited state, its spin doesn't flip relative to the electron it left behind. They still have opposite spins.
Okay, still opposite.
But in a triplet state, something else happens. The excited electron does flip its spin, so now it has the same spin as the electron back in the lower orbital. They become parallel.
Ah, so parallel spins in a triplet.
Exactly. And that seemingly small difference in spin state fundamentally alters the molecule's energy, its lifetime, and crucially how it reacts. It opens up completely different reaction pathways compared to the singlet state or the ground state.
Interesting. So how do chemists actually control this? What kind of light sources do they use?
Well, common sources are things like mercury vapor lamps. They emit light at very specific wavelengths like 254 nanometers, 313, 366. Very useful lines.
Because different molecules absorb different wavelengths.
Precisely. You need to match the light source to what your molecule actually absorbs. Sometimes you use filters to select just one wavelength. Standard glass cuts off UV below about 300 nanometers, but quartz lets you go much lower, down to 200.
And lasers. You mentioned lasers earlier.
Right. Lasers are key for studying the really fast stuff. They give you incredibly intense pulses of light at a very specific wavelength, often for just femtoseconds or picoseconds.
Yeah.
That lets you watch these reactions unfold in real time, almost.
Femtoseconds.
Oh.
That's mind-bogglingly fast.
It is. We're talking 10 to the minus 15 seconds. And the energy involved is significant. We can calculate it. E equals h nu, Planck's constant times frequency. Or, more practically for chemists, using wavelength, the energy in kilocalories per mole is about 28,600 divided by the wavelength in nanometers.
So that 254 nanometer light.
That works out to about 112.6 kilocalm. That is a lot of energy. Enough energy, in fact, to break most single chemical bonds, like a carbon-carbon or carbon-hydrogen bond.
Wow, okay, so that's way more energy than just heating things up gently.
Absolutely. It's a localized burst of energy delivered right to the electrons, opening up reaction channels that require overcoming huge energy barriers barriers that are insurmountable thermally. That's the core power of photochemistry.
Okay, so the molecule absorbs the photon. What happens in that instant? You said three key things.
Right. It's almost simultaneous. First, as we said, the electron gets promoted, usually HOMO to LUMO. Second, the Frank-Condon principle. This is crucial. At the very instant the light is absorbed, only the electrons rearrange. The much heavier atomic nuclei, they basically stay put. They retain their ground state geometry for that infinitesimally short moment.
So the molecule's shape doesn't change immediately.
Not in that exact femtosecond of absorption. It's called a vertical transition on energy diagrams because the geometry coordinate doesn't change. This means the molecule initially lands in an excited state that's geometrically unstable. It's not at its energy minimum for that excited state.
Ah, so it's like vibrationally hot.
Exactly. And it very rapidly, maybe in less than 50 picoseconds, relaxes. It sheds that excess vibrational energy as heat, usually to the surrounding solvent molecules, settling into the minimum energy structure of the excited state. This relaxation process is called internal conversion.
Okay, internal conversion. Got it. And the third point?
Spin conservation. The initial excitation doesn't involve electron spin flips, so the first excited state formed is always a singlet state. The spins remain opposite.
Always singlet first.
Always singlet first upon absorption. If the molecule is going to end up in a triplet state, that requires a separate subsequent step where one electron flips its spin. That process is called intersystem crossing.
Intersystem crossing. From singlet to triplet.
Yes, or potentially from triplet back down to singlet ground state later. It's generally slower than internal conversion within the same spin state manifold.
Okay, so the molecule is now in an excited state. Maybe singlet, maybe it crossed over to triplet. What happens next? Does it just sit there?
Oh no, it's highly energetic and usually very short-lived. It's now at a crossroads with several competing pathways available. It could undergo that intersystem crossing ISC to the triplet state if it hasn't already.
Right.
It could simply decay back to the ground state without reacting. This can happen non-radiatively, just dissipating all the energy as heat via internal conversion. Or it can happen radiatively by emitting a photon.
Emitting light.
Yes. If it emits light while decaying from the singlet excited state, S1, back to the ground state, S0, that's fluorescence. It's usually quite fast, nanoseconds maybe. Think of the quick glow of many dyes.
Like in highlighter pens.
Sort of, yeah. If it first crosses to the triplet state, T1, and then emits light decaying back to the singlet ground state, S0, that's phosphorescence. This involves a spin change, which is forbidden or slow. So phosphorescence is much slower, milliseconds, seconds, even minutes. That's your glow-in-the-dark stuff.
Ah, okay. Fluorescence fast, phosphorescence slow. Makes sense.
And, of course, the most interesting pathway for us chemists is that the excited state, either the singlet or the triplet, undergoes a chemical reaction. It forms new bonds, breaks old ones, rearranges.
So which state reacts, singlet or triplet?
It really depends on the specific molecule and the conditions. It's a race. If the singlet state can react very quickly, maybe faster than intersystem crossing happens, then the reaction proceeds from the singlet. If intersystem crossing to the triplet state is very fast, and the triplet state itself is reactive, then the reaction will happen from the triplet. Often, triplets live longer than singlets, giving them more time to react.
Okay. Now, what was that about photosensitization? You don't always have to hit the target molecule directly.
Correct. Photosensitization is a clever trick. You use a different molecule, the sensitizer, which absorbs the light efficiently. This sensitizer gets excited, often undergoes very fast intersystem crossing to its triplet state.
Okay, the sensitizer is now an excited triplet.
Right. Then, if it bumps into your reactant molecule, and if the sensitizer's triplet energy is higher than the reactant's triplet energy, it can transfer that energy. Bang. The sensitizer goes back to its ground state, and your reactant is now popped up into its triplet excited state, ready to react.
It's like a chemical game of tag with energy.
Pretty much. It's a great way to get reactions to happen specifically from the triplet state, even if direct excitation or intersystem crossing isn't efficient for the reactant itself.
And quenching is the opposite.
Essentially, yes. Quenching is any process that deactivates the excited state you're interested in. It could be energy transfer to another molecule, the quencher, which then dissipates the energy harmlessly. Or it could be electron transfer or some other interaction. It basically stops the photochemical reaction you want. Sensitization and quenching are physically the same energy transfer process, just viewed from different perspectives.
How do you measure how well these reactions work? Like how efficient are they?
We use a term called quantum yield, usually represented by the Greek letter phi. It's simply the fraction of molecules that undergo a specific process, like forming a product, divided by the number of photons absorbed by the reactant.
So if phi equals 1,
That means every single photon absorbed leads to one molecule of product. It's 100% efficient in that sense. Often, quantum yields are much lower, maybe zero point 0.1 or 0.01, meaning only 10% or 1% of absorbed photons lead to product.
can it be more than 1?
Yes, in chain reactions. If the initial photochemical step generates a reactive species that then goes on to react with multiple ground state molecules in a chain mechanism, the overall quantum yield for product formation can be much greater than 1. One photon triggers many reactions.
Cool. So, summing up this part, why are photochemical reactions so unique and powerful?
Well, 3 main reasons, I'd say. 1, the sheer excess energy. As we saw, light delivers a lot more energy than typical heating, enabling highly endothermic reactions that just wouldn't go thermally.
All right, breaking strong bonds.
2, accessing electronically forbidden pathways. Populating those antibonding orbitals changes the rules of reactivity, allowing transformations that orbital symmetry rules, for instance, forbid in the ground state.
Like turning forbidden reactions into allowed ones.
Exactly. And 3, the nature of the excited states themselves. Both singlet and triplet excited states have unpaired electrons. This gives them radical-like character, leading to intermediates, like the radicals, that are just not typically accessible under thermal conditions. This opens up a whole new world of chemical reactivity.
And you mentioned something about conformers, shapes of molecules.
Ah, yes, the Nair principle non-equilibrium of excited rotamers. Unlike thermal reactions, where molecules usually have time to wiggle around and react from their most stable shape, photochemical reactions are often so fast that the molecule reacts from whatever conformation it was in when it absorbed the photon. The excited state conformers aren't necessarily in equilibrium, which can dramatically affect which products form.
Fascinating. So how do chemists visualize all this complexity, these energy levels, transitions, reactions?
We use potential energy diagrams, often called Jablonski diagrams, when showing the different states and transitions like absorption, fluorescence, ISC, etc. And for understanding the reaction pathways themselves, we map out potential energy surfaces.
Surfaces, like landscapes the molecule travels on.
Kind of, yeah. You can imagine plotting the molecule's energy versus its changing geometry, like bond lengths or angles. The ground state has its surface, the excited singlet S1 has its own, the triplet T1 has another. Excitation is a jump up to an excited surface. Then the molecule moves around on that surface, maybe jumps between surfaces via internal conversion or intersystem crossing, and eventually finds a path down to products or back to starting material.
And those funnels you mentioned, conical intersections.
Right. Conical intersections, CIs, are absolutely critical. Think of them as points or seams where two potential energy surfaces offer an excited state and the ground state, or two excited states actually touch or cross. They act like literal funnels, allowing for extremely fast, non-radiative transitions between electronic states.
So it's how the molecule gets back down in the excited state efficiently.
Very often, yes. Instead of slowly emitting light or dissipating heat vibrationally, the molecule hits a CI and can just plummet back to the ground state surface very, very quickly. Crucially, the geometry at the conical intersection often dictates which way the molecule goes after the transition. It might land on the ground state surface, heading towards product A or product B, or even back towards the starting material.
So the CI is like a crossroads.
Exactly, a very important crossroads. They are kind of like the transition states of photochemistry, but they're geometrically more complex. Understanding the structure and location of these CIs is key to predicting and explaining photochemical outcomes. Computational chemistry has become invaluable for mapping these out.
Okay, that's a solid foundation. So we've explored the general principles: absorption, excited states, energy transfer, CIs. Now let's see this stuff in action. Where should we start? Maybe with simple alkenes.
Perfect place to start. Alkenes molecules with carbon-carbon double bonds show some classic photochemical behavior. And this is where we really see that amazing complementarity between photochemical and thermal reactions.
Complementarity. You mean they do opposite things?
Often, yes. What's typically forbidden thermally, like certain cycloadditions or electrocyclic reactions, becomes allowed photochemically, and vice versa. It's like flipping the rule book, often dictated by those orbital symmetry principles, the Woodward-Hoffmann rules, for example.
Okay, so what's a classic alkene photoreaction?
Cis-trans isomerization. Probably the most characteristic one. If you have an alkene like stilbene, which exists as cis-Z, and trans-E, isomers. Shining light on it causes the double bond to isomerize. You can interconvert them.
So you can turn trans into cis, even if cis is less stable.
Yes, that's a key synthetic application. Because both isomers absorb light and can reach a common twisted excited state, you often end up with a mixture called a photostationary state. The composition of this mixture depends on the relative absorption strength of the two isomers at the wavelength you're using and the quantum yields for isomerization in each direction. You can often enrich the thermodynamically less stable isomer this way.
How does it happen? What's the mechanism?
It usually proceeds via an excited state, could be singlet or triplet, where the geometry around the double bond is twisted by about 90 degrees. This twisted geometry is often the minimum energy point on the excited state surface. From this twisted state, the molecule can decay back down to the ground state surface, and when it does, it can land as either the cis or the trans isomer.
So the twist is the key intermediate point.
It is, and the exact nature of that twisted state and the subsequent decay often involves those conical intersections we talked about. Computational studies, like on ethene or styrene, show these excited states can be quite complex, sometimes pyramidalized, sometimes even having zwitterionic character, meaning charge separation.
Stilbene's a famous example, right? Z and E isomers.
Classic example. Direct irradiation usually involves the singlet state. You can use different wavelengths to favor one isomer in the photostationary state because the E and Z isomers absorb light differently. You can also use photosensitization to go via the triplet state, and depending on the sensitizer's energy, you can, again, control the final Z-E ratio.
And it's not just isomerization, right? Stilbene does other things.
Right. The Z-stilbene, upon excitation, can also undergo an electrocyclic reaction to form 4A,4-Abi dihydrophenanthrene. This competes with the isomerization. This cyclized product is often unstable, but can be trapped, for instance, by oxidation.
Okay, what about other alkenes? Simple ones.
Unconjugated alkenes, like just simple cyclohexene, usually need shorter wavelength UV light. They also do cis-trans isomerization if possible, but they can also undergo 2+2 cycloaddition to form dimers, especially if concentrated. Diluting them favors isomerization. Sometimes you see rearrangements too, like hydrogen shifts leading to carbenes or alkyl shifts.
Carbenes from alkenes.
It seems so. Computation suggests that conical intersections involved in the decay of excited alkenes can have structures resembling carbenes or radical species, leading to these unexpected rearrangements. For cycloalkenes like cyclohexene or cycloheptene, the ring strain prevents full twisting, leading to unique reactions. You can get ring contraption, or sometimes if you use hydroxylic solvents like methanol, you can actually trap a highly strained trans-cycloalkene intermediate.
A trans double bond in a six-membered ring. That sounds incredibly strained.
It is hugely strained, but photochemistry can generate it fleetingly, and it reacts very quickly, for example, by adding methanol to relieve that strain.
What about conjugated dienes, like butadiene?
They also isomerize, but interestingly, the singlet and triplet states behave differently. The triplet state acts like a diradical where rotation can happen easily at both ends, but the singlet state seems to retain more double bond character, maybe isomerizing via a structure where only one end can easily rotate. Again, it highlights how different excited states have different structures and reactivities.
This brings us back to orbital symmetry and those Woodward-Hoffmann rules. How do they explain these photochemical reactions?
They provide a powerful framework. Take the 2p-pi plus 2p-pi cycloaddition of two ethene molecules to form cyclobutane. Thermally, this is forbidden by orbital symmetry rules. The orbitals just don't overlap correctly in the ground state to allow a smooth, low-energy reaction. You'd have to go through a very high-energy intermediate.
But photochemically?
Photochemically, it's allowed. If one ethene is in its excited state, say S1, and the other is in the ground state, the orbital symmetry does allow for a favorable interaction, leading to the cyclobutane product. The excitation effectively changes the symmetry properties of the interacting orbitals.
So light flips the switch from forbidden to allowed?
In many cases, yes. Same for electrocyclic reactions. For example, the ring opening of cyclobutene to butadiene. Thermally, it proceeds with a specific stereochemistry called conrotatory. Photochemically, the rules predict the opposite stereochemistry, disrotatory.
And does it actually work out that way?
Mostly, yes. The photochemical electrocyclization of dienes to cyclobutenes, or the ring opening of cyclohexadienes to hexatrines, generally follows the predicted stereochemistry. It's remarkably consistent. However, there are subtleties. The simple orbital symmetry rules assume perfectly concerted reactions, but we now know that many photochemical reactions proceed through multiple steps involving excited state transformations and conical intersections, which can sometimes complicate the simple picture. For instance, the photochemical ring opening of simple cyclobutenes isn't always perfectly stereospecific, likely because of decay dynamics near a conical intersection.
Okay, so the rules are a great guide, but reality can be complex. What about that other rearrangement you mentioned, the dipymethane?
The dipymethane rearrangement. This is a really fascinating and quite general photochemical reaction. It happens in molecules that have two pi systems, like two double bonds, or a double bond in an aromatic ring separated by a single sp²-hybridized carbon atom, like a 1-4 structure.
Okay, two pi systems separated by one carbon. What happens?
Upon irradiation, the molecule rearranges to form a vinyl cyclopropane derivative. The mechanism is often depicted as forming a three-membered ring by bridging two of the carbons involved in the pi systems, creating a cyclopropyl diradical intermediate. This then opens up differently to form the final product.
A diradical intermediate again?
Often, yes. Though the singlet reaction might sometimes be concerted. It's stereospecific in certain ways. The configuration of substituents on the double bond that doesn't migrate is usually retained, and the central sp³ carbon often undergoes inversion of configuration.
Does it work better with certain groups attached?
Definitely. Substituents that stabilize radical character tend to favor the reaction. For instance, if you have phenyl groups on the ends, the reaction works well. It generally proceeds so that the more stable potential radical intermediate is formed during the rearrangement. It's a synthetically useful way to build complex cyclic structures.
Wow, that's a lot of action just from alkenes and dienes. But the fun doesn't stop there, right? Carbonyl compounds, ketones, aldehydes, they have their own photochemistry.
They absolutely do. The carbonyl group, CO, has its own unique electronic structure, leading to a distinct and incredibly useful set of photochemical reactions. Very important in synthesis and even in understanding things like photodegradation.
So what happens when a ketone absorbs light?
In simple aliphatic ketones, the most important excited state is often the N-pi state. This involves promoting one of the non-bonding electrons located primarily on the oxygen atom up into the pi star anti-bonding orbital of the carbonyl group.
Into pi star. Okay.
Yes. This initial S1 state is formed, but for many ketones, especially alkyl ketones, intersystem crossing to the corresponding T1 triplet state is very fast and efficient. So much of the observed photochemistry of simple ketones actually happens from the N-pi triplet state.
And what does that N-pi state look like? How does it behave?
It's quite different from the ground state. The molecule often becomes non-planar, pyramidal at the carbonyl carbon. The CO bond lengthens. Importantly, the electron distribution changes, having one electron in the non-bonding orbital on oxygen and one in the pi star orbital gives the oxygen atom character similar to an alkoxyl radical, and the carbon gets some radical character too. It becomes much more reactive, especially towards hydrogen abstraction.
Hydrogen abstraction, like stealing an H atom.
Exactly. This is one of the two most common reactions of excited carbonyl. The radical-like oxygen in the N-pi state can pluck a hydrogen atom from another molecule nearby, maybe the solvent, or even from another part of the same molecule if the geometry is right. This is called intermolecular or intramolecular hydrogen abstraction.
What's the other main reaction type?
That's alpha cleavage, also known as the Norrish type reaction. Here, the bond between the carbonyl carbon and one of the atoms attached to it, the alpha carbon, breaks homolytically, forming two radicals.
So either grab an H atom or break the bond next door.
Those are the big two for simple ketones. Let's take benzophenone photoreduction as a classic example of hydrogen abstraction. You shine light on benzophenone and a solvent like 2-propanol. The benzophenone gets excited to its triplet state, then abstracts a hydrogen atom from the alcohol, forming a kettle radical. Two of these kettle radicals then combine to form a pinacol product.
And this happens from the triplet state. How do we know?
Several lines of evidence. It shows an isotope effect if you use deuterated donors. It can be quenched by known triplet quenchers. You can directly observe the intermediate radical using flash photolysis techniques. And interestingly, in pure 2-propanol, the quantum yield can be up to 2.
2. How?
It's a chain reaction. The radical formed from 2-propanol can actually transfer a hydrogen atom back to a ground state benzophenone molecule, regenerating the kettle radical and continuing the chain. So one photon absorption leads to the reduction of 2 benzophenone molecules.
Clever. What about intramolecular H abstraction?
That happens if the ketone has hydrogen atoms in the right position, usually on the gamma carbon. 3 carbons away from the CO. This leads to the Norrish type 2 reaction. The excited carbonyl oxygen grabs that gamma hydrogen through a 6-membered ring transition state, forming a 1-thioisor diradical intermediate.
Another diradical.
Yes. And this diradical has 2 main fates. It can cleave the bond between the alpha and beta carbons, yielding an alkene and a smaller enol, which tautomerizes to a ketone. Or it can cyclize to form a cyclobutanol derivative. Usually cleavage is the major pathway.
Okay, type I is alpha cleavage. Type 2 involves gamma hydrogen abstraction followed by cleavage or cyclization. Got it.
And alpha, beta unsaturated ketones, they have their own interesting photochemistry too, often involving cycloadditions with alkenes, which is synthetically very important. Or they can undergo rearrangements.
Rearrangements too, like the d-pi-methane.
Similar ideas apply. Cyclic enones, for instance, can undergo the Lumictone rearrangement, or sometimes a type of d-pi-methane rearrangement, depending on the substituents. Beta, gamma unsaturated ketones often do an oxy-pi-methane rearrangement. It's really a rich field. The exact outcome is super dependent on the specific structure of the starting ketone.
It sounds like it. Okay, we've covered alkyl enones, carbonyls. What about the king of stability, benzene? Do aromatic rings get in on the photochemical action?
They absolutely do. Despite their aromatic stability in the ground state, excited aromatic compounds undergo fascinating photosomerizations and cycle additions. It's another prime example of how excitation changes the rules.
So what happens if you just shine UV light on benzene itself?
If you irradiate liquid benzene, say at 254 nanometer, you don't get a huge amount of reaction, but you do form small amounts of products like fulvene, and, more interestingly, benzoylene. Benzoylene is a highly strained, non-aromatic isomer of benzene with a bicyclic structure. It's quite reactive.
A non-aromatic version of benzene.
Exactly, a valence isomer. It's thought to form via 1/3 bonding across the ring in the excited state, creating a diradical intermediate that then closes up. If you have bulky groups on the benzene ring, like T-butyl groups, these photochemical isomerizations can become much more efficient, leading to various interesting bicyclic or tricyclic structures.
What about reactions with other things, like benzene plus an alkene?
That's a really important class of reaction. Irradiating an alkene in the presence of benzene can lead to photocycloaddition. Usually, the main product is a 1.1 adduct, where the alkene is added across the 1-3 or meta positions of the benzene ring.
Meta addition, that's unusual.
It is. Thermally, you'd expect addition across adjacent positions. This photochemical metacycloaddition is thought to proceed through an exaplex, a short-lived excited state complex formed between the excited benzene molecule, usually singlet state, and the ground state alkene. The geometry of this exaplex leads to bonding at the 1 and 3 positions.
And is it specific? Like, does the alkene geometry matter?
Often, yes. The reaction can be stereospecific with respect to the alkene geometry, suggesting a concerted or near-concerted process after the exaplex forms. You can also get some 1,2 ortho or 1,4 addition products, but meta is often dominant. Substituents on the benzene ring can influence the regiochemistry too.
So even stable aromatic rings can be coaxed into pretty weird reactions with light.
Definitely. It highlights again that the excited state behaves very differently from the ground state. Aromaticity is a ground state concept. The excited state doesn't necessarily play by those rules.
This is all incredibly complex.
Yeah.
How do chemists really figure out what's going on in these ultra-fast fleeting moments? You mentioned computation earlier.
Yes, computational chemistry has become absolutely essential for understanding photochemistry. It allows us to kind of see the structures of these short-lived excited states and, crucially, map out the potential energy surfaces and locate those critical conical intersections.
So what have computations told us about, say, butadiene that we didn't know before?
They've given us much more detailed pictures. We used to talk about simple diradicals, but computations show these excited states and CIs often have very specific geometries, twisted, pyramidalized, sometimes with significant charge separation. It's with turionic character mixed in. For butadiene, calculations help visualize how excitation leads to different possible structures, like twisted allyl methylene diradicals in the triplet state, or more complex, tetraradical structures near conical intersections in the singlet manifold.
Tetraradicoid, like 4 unpaired electrons.
Effectively, yes, near certain CI geometries. These computational models show points on the energy surface where multiple bonds are partially broken, and the electrons are essentially unpaired before they decide how to repair as the molecule relaxes down to the ground state. This helps explain why you can get multiple products like cyclobutene or bicyclobutane, or even fragmentation from the same excited state precursor. It all depends on the dynamics as the molecule passes through or near that CI.
So the CI structure really dictates the outcome.
It plays a huge role. Computations can model the minimum energy paths leading away from a CI and predict branching ratios between different products, often matching experimental observations remarkably well. They've been applied to understand the stereochemistry of electrocyclic reactions, the competing pathways in hexatrene photochemistry, and even the rearrangements seen in systems like cyclooctatrene.
It sounds like computation is really unlocking the secrets behind these reactions.
It truly is. It provides a level of detail about these ultrafast events and transient structures that's incredibly hard, sometimes impossible, to get purely from experiments. It helps refine our mechanistic models from simple arrow pushing to a much more nuanced understanding of energy surfaces and dynamics.
Wow. Okay, what a journey through the world of light-driven reactions. From that initial absorption of a single photon, all the way through excited states, singlets, triplets, those crucial conical intersections, and the amazing variety of reactions, isomerization, cycloadditions, fragmentations, rearrangements. It's really a whole different branch of chemistry.
It really is. We've seen how the basic principles, like the Frank-Condon principle, play out. We've looked at classic alkene reactions like cis-trans isomerization, the power of orbital symmetry in 2+2 cycloadditions, and electrocyclic reactions, that unique d-pi methane rearrangement. Then the distinct behavior of carbonyls with their N-pi states leading to hydrogen abstraction and cleavage, and even how stable aromatics can be forced into unusual reactions.
And what really strikes me is how these aren't just, lab curiosities. You've mentioned several times how useful these are in synthesis.
Absolutely. Photochemistry provides routes to molecules and structures that are difficult or impossible to make using traditional thermal methods. Think about accessing strained rings, controlling stereochemistry in unique ways, or creating specific isomers selectively. These are powerful tools in the synthetic chemist's toolbox, used in making complex natural products, new materials, pharmaceuticals. It's very practical.
And the sheer speed. Femtoseconds. It just blows my mind. It really makes you wonder, doesn't it? What other chemical secrets are just waiting for the right wavelength of light to unlock them? How can we harness this power even more precisely? Maybe for greener chemistry, using light instead of harsh reagents. Or for designing light-activated drugs.
Those are exactly the kinds of frontiers researchers are exploring, using light for catalysis, developing new photoresponsive materials, understanding biological photoreceptors. It's a field that's constantly evolving and full of surprises. There's still so much to discover about how light and matter interact at the molecular level.
It's definitely given me a new appreciation for light. We hope this deep dive into photochemistry has, illuminated some fascinating new corners of chemistry for you too. Thank you so much for joining us on the deep dive.